Large language models have exhibited remarkable progress across various domains, demonstrating their potential to revolutionize natural language processing and artificial intelligence applications. Test time scaling has emerged as an important technique for further enhancing the performance of LLMs by strategically allocating additional computation during the inference phase. This approach enables LLMs to achieve improved accuracy and efficiency, particularly in complex reasoning tasks. TTS encompasses a range of methods designed to optimize the computational resources utilized by LLMs during inference. These methods can be broadly categorized into two main types. Internal TTS. In this approach, LLMs are trained to engage in a more deliberate thinking process, employing techniques such as chain of thought to break down complex problems into smaller, more manageable steps. This internal deliberation allows the model to explore different reasoning paths and arrive at more accurate solutions. External TTS. This approach involves the use of external mechanisms, such as sampling or search-based methods, to guide the LLM's response generation process. By strategically exploring different response options, external TTS methods aim to select the most promising solutions while minimizing computational overhead. Despite the potential of TTS, several challenges remain in fully understanding and effectively utilizing this technique. One of the primary challenges is determining the optimal approach to scale test time computation across different policy models, process reward models, and problem difficulty levels. This paper addresses two core research questions. Optimal scaling strategy. What is the most effective way to scale test time computation, considering the specific characteristics of the policy model, PRM, and the complexity of the problem? Performance boundaries. To what extent can extended computation improve the performance of LLMs on challenging tasks, and can smaller language models outperform larger ones through this approach? To investigate these questions, the authors conducted comprehensive experiments on two mathematical reasoning datasets. Math 500. This dataset comprises 500 representative problems from the math dataset, designed to assess mathematical problem-solving abilities. American Invitational Mathematics Examination 24. This dataset consists of challenging problems from the American Invitational Mathematics Examination, requiring advanced mathematical reasoning skills. The experiments involved a range of policy models and PRMs, with varying sizes and architectures. The policy models included LLMs from the Llama 3 and Qwen 2.5 families, while the PRMs spanned different model series with sizes ranging from 1.5 billion to 72 billion. The experimental results yielded several significant observations. Dependence on task and model characteristics. The compute-optimal TTS strategy was found to be highly dependent on the choice of policy model, PRM, and problem difficulty level. This highlights the importance of tailoring TTS strategies to the specific requirements of each task and model. Outperformance of smaller models. With the compute-optimal TTS strategy, extremely small policy models were able to outperform larger models on complex reasoning tasks. For instance, a 1 billion LLM surpassed a 405 billion LLM on the Math 500 dataset. Similarly, a 3 billion LLM outperformed a 405 billion LLM on both Math 500 and American Invitational Mathematics Examination 24, while a 7 billion LLM exceeded the performance of state-of-the-art reasoning models like O1 and DeepSeek R1. Efficiency gains. Compute-optimal TTS not only improved accuracy, but also led to significant efficiency gains. Smaller models with TTS achieved comparable or better performance than larger models while requiring less computational resources. Based on their findings, the authors propose a reward-aware compute-optimal TTS strategy. This strategy takes into account the influence of rewards in the TTS process, ensuring that the compute-optimal scaling adapts to the policy model, prompt, and reward function. Future research directions include extending TTS to a wider range of tasks, such as coding, chemistry, and other domains requiring complex reasoning. Exploring more sophisticated methods for compute-optimal TTS, potentially incorporating reinforcement learning and other advanced techniques. Investigating the theoretical foundations of TTS to gain a deeper understanding of its capabilities and limitations. By addressing these challenges and pursuing further research, TTS can play a crucial role in unlocking the full potential of LLMs and driving innovation in artificial intelligence.